behalf of our department and the School of Science and Technology, I would like to thank you all for attending this lecture. I would like also to thank Untitled Technologies for sponsoring this lecture series since the start in 2006. Before I start, yeah, let me just switch to. By Dr. Roger Steinfleet, who is the CTO for Microwave Measurements by Untitled Technologies, and the title of his talk is Microwaves for Imaging, a new modality for medical diagnosis, process analytics, and nanoscale visualization. Our guest speaker for today has joined Broadcom through its acquisition of Technovas. I don't know what's happening. Of Technovas Incorporated, where he served as the chief scientist. He has done extensive research in areas of traffic management and quality of service in access networks. Glenn chairs the IEEE P1904.1 working group that develops a standard for service interoperability in EPON. EPON stands for, by the way, the Internet Passive Optical Network. Prior to Technovas, Glenn worked at the Advanced Technology Lab at All Optics Incorporated, where he was responsible for design and performance analysis of passive optical network scheduling protocols, and was involved in prototyping the very first EPON system. Dr. Craner received his Master of Science and PhD degrees in computer science from UC Davis, where he was awarded the National Science Foundation grant to study next engineering broadband access networks. He has authored 16 patents. His book, Internet Passive Optical Networks, has been published in English by McGraw-Hill and also in Chinese. By the way, he was, I would like to thank him. He gave me a copy of his book. Those of you who are interested, you can get it from. What I'll do is that I'm just let me pass it from that just to class. Okay. So here is Dr. Craner.
I have one more book. I'll give it for presentation. Please think of something. How to switch back?
I will do it for you right now. I hope it will not drop you on the slideshow.
I'll try to focus in my talk not so much on details of technology, how we solve things, but rather what are the problems that we're trying to solve. And I'll start with a true story. Sometime in 2008, Comcast tried to fit more channels in bandwidth that they have available on their coax network. What they did is simply increase compression ratio on video channels. A subscriber who happened to have both Fios from Verizon and cable connection from Comcast recorded both programs, same programs on both channels. One from fiber optic network from Verizon, one from Comcast, and compared the results and posted in a blog on internet. And it really became nightmare scenario for Comcast. People saw how quality, and unfortunately projector here is really low quality, but on the blog, if you go to this blog, you will see significant difference in quality of video. And the guy captured many programs, Discovery Channel, Entertainment, National Geographic. Everywhere there was difference. And fallback was huge from users, from viewers. You can see people commenting on that blog that as soon as Fios comes to my area, I'm switching from Comcast. How can they do that? This is not acceptable. And really, we know in areas where Verizon competes with Comcast, Comcast bleeds subscribers significantly. Subscribers leave cable companies in thousands, join Verizon, simply because Verizon offers more benefits, significantly more benefits using fiber optic. So operators today are forced to upgrade their network just to prevent mass exodus of users. If they do nothing, they will lose all subscribers, they lose revenue completely. Not only operators need to upgrade their networks, but significant portion of their revenue is being taken by what's called over-the-top providers. These are companies that don't own networks, but provide services that users like. For example, look at Skype. Skype, in 1 year ago, in third quarter of 2009, had almost 28 billion minutes of Skype-to-Skype conversation. That's 28 billion minutes that operators like AT&T or Verizon didn't get revenue for. Skype had 9.2 billion minutes of video calls in 1 quarter, 3.1 billion minutes of Skype to phone calls. So this is really what takes revenue away from traditional telcos. 8% of all international calls are now being done on Skype. This is huge. YouTube serves in a single day 1 billion videos. Imagine what traffic that generates on the network. 35,000 hours of video is uploaded daily. Netflix recently announced, actually not Netflix, another company did research. Netflix today is responsible for 20% of all North America network traffic in peak hours. These are huge volumes. So if people watch videos, movies on Netflix, they're not watching them on cable networks. So all those revenues, these are all unfulfilled revenues for traditional operators. So infrastructure owners are trying to compete. How? By trying to sell services. For example, AT&T has Uverse service, where they try to sell video. KDDI in Japan has similar service called Hikari Plus, Optical Plus. Hana TV in Korea, Fios in Verizon. All those are traditional telephony operators that are trying to become video providers as well. But the question is, can they really win? And to win, they need two things to happen. One, they need to provide innovative applications that at least match what over-the-top companies can provide. It should be smart, it should be integrated, it should be voice and messaging and visual all integrated, basically as convenient as you can get it from Skype or Netflix or any other provider. But this is only part of the equation. This will only put them on level field with over-the-top providers. It will not be a winning solution yet. To have a winning solution, they need to provide superior user experience. And they can do it because they own the network. Consumers already know what they expect from good network. If they see IPTV with quality way below what they get on cable network, they will leave. They will not stay with such provider. If voice over IP quality is below what they get with regular phone, they will not use that service. So there is some intrinsic benchmark there. But point of all of that is network should become application aware. And it should be able to enforce end-to-end quality of service required by different applications. If operators don't do it, there is absolutely nothing that will differentiate them in eyes of subscribers from companies that don't own the network. So to achieve that, they need networks. They need to deploy networks that satisfy three requirements. And all these three requirements are equally important. One is network should be low cost. If you consider long-haul network, for example, a connection that connects US and Asia, that goes under the Pacific Ocean, it aggregates millions or hundreds of millions of flows or subscribers. So the cost of that connection shared by that many paying subscribers. If you look at the macro network, it may aggregate traffic from hundreds of thousands to millions of subscribers. So cost of that network is shared by so many subscribers. If you look at access segment is something that connects your house or your dorm room to network provider. It aggregates traffic from hundreds, in good situation, hundreds of subscribers, sometimes even less. So cost of access network is extremely important. When I talk about cost, it's not just how much equipment costs to operator to purchase. It's also how much power is consumed, what the lifetime of this equipment, and how easy it will be to upgrade this network when time to upgrade comes. Second important requirement is high capacity. Access networks today, leading access networks, they share 1 gigabit per second among maybe 32 or 64 subscribers, and they're already running out of bandwidth. So more bandwidth required because next generation services always bandwidth hungry. I'll speak more about this later. Bandwidth by itself is competitive factor. So operators are forced to upgrade networks, and bandwidth is one of the factors. But also, as I mentioned, to be able to regain revenue from over-the-top providers, they need to provide quality of service. Different services require different performance from the network. IPTV, for example, needs lots of bandwidth. It generates very bursty traffic. It is very sensitive to packet loss and jitter. Voice over IP does not need as much bandwidth, but is extremely sensitive to loss as well and delay. Service isolation is very important. If someone is watching video and the neighbor is downloading big file, the video should not be affected. Similar way in the other direction. If I'm watching video and my neighbor downloads big files or uploads big files, my video should not starve his service as well. QoS cannot be solved with just throwing more bandwidth in the network. To give you an example, when DOCSIS 1.0 was developed, this is cable network standard, it was network with most bandwidth at its time, most high-speed network at that time, yet it could not support even a single voice over IP call because that network did not provide any service isolation, any QoS. So your voice packets may get queued behind data packets, may get lost if queue is full, and voice service didn't work, voice over IP. So Cable Labs quickly realized that problem and started working on DOCSIS 1.1, which fixed it. It added various QoS mechanisms, and DOCSIS 1.1 could reliably support voice over IP services. So now I will go over all these 3 points and discuss how to design network that satisfies these requirements. How do we design for low cost? And it's better to start other roads merging in, no other traffic on it. Why it's ideal? Because I know exactly at what time to leave, so I can be in the office by 9 a.m. Delay is absolutely constant, nothing can affect me on my way. I can drive anything I want. I can drive big rig if I want to, or a bicycle. Whatever I put on the road, same thing will arrive to my office. That is my lean preserved shape of my traffic. So it's ideal, but it is not practical. Why it's not practical? Because construction cost for such network is prohibitive. I cannot construct, or no municipality can construct private road for every house. What's interesting, size of companies in this architecture would be very limited because of how many roads a building can terminate. You simply cannot accept more employees because there are no more roads that can be terminated by the building. It's a funny example, but it's actually a real problem that happens with some network architectures. So, as we see, ideal network is not practical. Consequently, practical network is not ideal. In practical network, I need to share my resources. I need to share roads so that many employees can share same road and get to a company through one entrance. Why it's not ideal? Because now there should be some kind of arbitration protocol, maybe traffic light or stop sign, so that different cars are not colliding. Because of that arbitration protocol, delay is not constant anymore. So there is some variability in the way. And also in some networks, what may happen, you may leave your house in big rig, but along the way it's get chopped in small little cars that you arrive in many small segments. When it fragments long packets into smaller packets. Very similar situation is in the network. Some companies promoted, some vendors promoted, and some operators started building network, which is exactly like this point-to-point private road. They had fiber optic cable going from network operator directly to a house. It's simple, it's ideal, it's very expensive. Central offices had huge problem of managing fibers. Size of central office was limited in that architecture to 5, 10,000 subscribers, while really one central office should support maybe 100,000 to 150,000. It's very expensive. A separate port is required for each subscriber, so such network consumes lots of power. But even when there is no traffic going on, when subscriber in the middle of the night, this network sends idles. This is how point-to-point networks operate. When there is no useful data, idle characters are going back and forth. All that consumes power, very inefficient network. So few providers that tried it quickly abandoned it. One way to solve the problem is to put aggregation switch in the field, close to subscribers. That helps because now central office can serve many subscribers. You have one port here, which later split and can serve hundreds of subscribers. But this architecture became very expensive. Why? Because that field in the switch, that switch in the field required power. So separate power lines should be laid down from substation to that location. It required backup power, so big batteries should be there. Maintaining was nightmare because for everything that would happen with this box, operator needed to see an alarm. If someone opens a door, there is alarm going to operator. Someone closes the door, alarm going to operator. If temperature is too high, alarm. Temperature too low, alarm. Often they would need to send repair crews or technicians to do various tasks on these boxes. As NTNT very well know, sometimes these boxes cannot handle bandwidth explosion, and that happens somewhere in the area. In this case, it's a joke, of course. In this case, there was faulty battery and it blew up and it damaged nearby house. But this is a real problem. Nevertheless, main expense here is providing power and maintenance of these boxes. So this architecture is not also very low cost, not as low cost as operators would like. So what comes next? Can we somehow combine best of two worlds? Can we have single port at central office, as shown here, but avoid having any switch in the field, as shown here? And the answer is yes, we can. And this is what has been done. Imagine that switch that is located in central office is simply broken in parts. And some of the parts are moved close to subscribers. And they're connected by fiber. There is nothing in between but a passive device called power splitter. You can see there is just one line that connects that many subscribers to central office. There is no equipment in the field. It just fork in the road. Fiber is fused together, and that means signal that goes downstream is split and identical signal goes to everybody. And when signal goes upstream, there is special protocol that allows it to reach central office without conflict, without collision. So that appeared as very, very beneficial architecture from cost point of view. One port in central office can serve many users, no power in the field. One fiber, so it minimizes fiber cost to deploy that network. Overall, it's lowest cost architecture. It works as a distributed switch, but switch which has nothing in between. All the intelligence is at the edges here, and in between is just a fiber. So that's conclusion number one, is PON is really designed for low-cost architecture. Point number two, how do we design for high capacity? To understand how to design better for high capacity, we need to understand what drives that high capacity. And this is a very interesting report recently released by Sandvine Corporation in Canada. In North America, median usage is 4 gigabytes per month, and mean is 15 gigabytes. And what that tells us that usage is heavily skewed toward few subscribers consuming most or generating most of the traffic. And indeed, if you look at that chart, you will see that 1% of all users generate 40% of traffic. That's huge asymmetry. This is just upstream. Downstream is not as much, but upstream is very important. In Asia Pacific, it's similar non-uniformity, but not to the same degree. It's 12 gigabyte median, and mean is 35 gigabytes. So usage in Asia is actually much higher than in North America. 97 hours is how long user is online per month. In US, 164 hours in Asia Pacific. So users really spend lots of time online, generate lots of traffic. Non-uniformity of user demand is a critical parameter when we design network. We need to always think that demand is not uniform. It's not that all users are asking for the same amount of bandwidth at the same time. Also, what drives bandwidth demand? Applications. From the same report, today almost 46% of all network data is real-time entertainment. Various video programs, teleconferencing. Netflix alone is responsible for 20% of North American network traffic in peak hours. This is huge for a company that's barely a few years old, 5 years old maybe. This is huge impact. And if you see at the trend with IPTV traffic, it consumes significantly more and more bandwidth. Standard definition IPTV channel required 2 to 4 megabit per second. High definition 8 to 12, and this is actually highly encoded high definition. It's MPEG-4. If you use something more commonly used, which is MPEG-2, it's twice as much. So it's 16 to 24, 22, 24. And then 3D high definition takes twice that much because in the simplest way, they simply send 2 streams. So the trend is that even if we stay online for the same amount as we stay today, the amount of traffic that we will consume a year from now will be significantly more, because the trend is to have richer applications that generate more and more traffic. So how do we engineer networks to support IPTV, to support video? This is a snapshot of 300 seconds of standard definition MPEG-2 coded video. And you can see that maximum is somewhere around 4 megabit per second. Sometimes there are gaps or lulls. Average, I would say, here would be slightly, probably around 3 megabit per second. But this is 3 seconds. Each point here represents aggregated traffic for 1 second. If I zoom in 100 times, and instead of 3 seconds, I look at just 3 seconds, instead of 300 seconds, I look at just 3 seconds, this is how my traffic looks like. Highly bursty, bursts reach 80 megabit per second when they arrive. And then between bursts, there is nothing. And this is just standard definition TV. If I look at high definition TV, situation will be even worse. In fact, bursts always reach maximum link capacity, and capacity for this test, link capacity was 100 megabit per second. So if I waited a little bit longer, I would see here bursts reaching all the way to 100 megabit per second, maybe lasting tens of milliseconds or so. Operators are not used to this traffic. This is not how voice traffic behaves. This is not how operators model their networks. They model it as average. And when I say here, it takes, standard definition takes 2 to 4 megabit per second, this is a very misleading number. Because if you really allocate just 2 to 4 megabit per second, it will not work very well. Because all these bursts will be either trimmed, what's called policing, they will be trimmed to allocated rate, or they will be delayed also to keep it within allocated rate. So there are 2 commonly used methods of policing where you discard packets which are over your desired rate, or shaping where you delay packets which are over your desired rate. In each case, the goal is to enforce the rate. You provision rate, and you tell that unit, I want my rate of packets not to exceed 2 megabit per second, and it will do either this or this. Well, both of these approaches are very bad for video. In case of policing, performance suffers because packets will be lost, and video cannot tolerate that very well. You will see pixelation, you will see frozen frames, and so on. If you delay, situation is not much better. Frame that arrives too late is useless. If your playout buffer is past that point where frame should be played out, it cannot use it. So frame that delayed significantly more compared to other frames will arrive, but too late, and will discarded. What is needed is some kind of adaptive traffic engineering. If shaping, traditional shaping, says, give me best possible delay, but ensure that my rate is enforced, new shaping is required which says, give me the best possible rate, but ensure that my delay is enforced. So here, you may delay frames a little bit, but not as much as in traditional shaping. And because you may delay them not as much, that means you need to send them faster. And if you send them faster, that means your rate is higher than in traditional approach. What I'm leading to is, want you to understand that providing fixed bandwidth is extremely inefficient. You need to be able to accommodate bursts as they're generated by applications. And in this case, this kind of adaptive traffic engineering will smooth bursts a little bit, but not completely. You still send bursts because you are trying to control delay. You're trying to enforce delay bound and not let any frame be delayed more than what video can use. Sharing of capacity is an extremely crucial advantage for any network, considering today traffic. You saw how bursty is traffic. Between bursts, you want this unused capacity to be given to someone else. Here's another test we did. This is example of 500 milliseconds of network traffic. We looked at simple queue where input to a queue was just point-to-point Ethernet line, 100 megabit per second with bursty traffic. Output from the queue was another link on which we would give that queue fixed slots. On input, we decided to make arrival rate only 20 megabit per second. That is, our input link was 20% utilized. Fairly low traffic, 20 megabit per second. We provided output capacity 50 megabit per second. So 2.5 times more than your input rate. That capacity was provided by giving that queue 6,250 byte slot every 1 millisecond. So fixed slot every 1 millisecond coming in takes number of packets from the queue and more packets meanwhile arrive. What this chart shows is red lines are slots that were underutilized. We gave that slot to a queue and slot went back empty, either completely empty or half empty, not filled completely because queue did not have enough data. This chart, green chart, shows queue size. And you can see that even though our output capacity by 2.5 times exceeded input rate, still our queue at some periods grew significantly, at one point even to 40 kilobytes were stored in the queue. So why is that? This happens because data arrives in big bursts. And when data arrives in big bursts, then all bytes in that burst are affected. And then between bursts there is nothing. So between bursts network is not utilized, but there are no bytes to enjoy that free ride. It's same as when you drive on freeway, it appears that freeway is always clogged. But really it's not. It's just because you drive during peak hours, back and forth. So you always see freeway busy because everyone drives at the same time. Same thing happens with networks. When bursts arrive, everyone is affected, and then between bursts, there is no traffic, and performance is good, but no one can see that good performance. So from data byte point of view, network is always busy. So here is that new technology that my company is building and selling. It's called Ethernet passive optical network. It uses one fiber which is split in many branches. We call it tree structure. This link called trunk, and these links are called branches. Downstream is just broadcast to everybody, and devices called ONUs, optical network units, selectively pick frames that destined to subscribers connected to ONUs. They send back traffic all toward a device called OLT, optical line terminal. This device is located in central office, in operator central office. All devices are arbitrary. If they all send data at the same time, data will collide and become corrupted. So OLT schedules each device to transmit data upstream at proper time. The scheduler is accomplished by exchange of messages. Message from OLT to ONU called gate. Think of it as it opens gate and passes less traffic through. And message from ONU to OLT called report, because ONU tells OLT how much data has accumulated since previous gate. In time domain, this is how transmission on PON looks like. Of course, we can have a very simple device where OLT would ignore all the reports and give each ONU fixed window size. Or we can have a more complicated design where OLT gives each ONU window precisely matching what ONU reported. If ONU says, I have 10,000 bytes, OLT will give it 10,000 bytes, not a byte more. And if another ONU says, I have only 1,000 bytes, OLT will give it window just for 1,000 bytes and not more.
How are we doing?
So here's another test we did. We compared performance of EPON with static slot assignment. Every ONU gets same and fixed amount versus dynamic slot assignment. In dynamic slot assignment, average packet delay improved in this particular test 66 times. This is huge improvement. This is, by the way, this is logarithmic scale. So delay here was about what, about 20 milliseconds, and here it was about 1 millisecond, 300 microseconds. Huge improvement. Same as queue size. Why? Because we didn't waste slots for ONUs that don't have traffic. We gave that empty space, empty capacity to ONUs that have traffic. That happens only because traffic is bursty. If you model this with constant bitrate traffic, you will see no difference at all. But real traffic is not constant bitrate. It's extremely bursty. So we have that picture. That huge improvement because of shape. Even more, we compared architecture where we had point-to-point links connecting subscribers to a switching central office. In this case, we had 32 channels. Each channel had 1 gigabit per second capacity. So total, this network had 32 gigabit capacity. Then we took new generation of EPON, where 10 gigabit capacity is shared among the same number of users, 32 users, but sharing 10 gigabit capacity. And traffic was very asymmetric, as I indicated earlier, non-uniform. That is, 10% of users generated 80% of traffic. And we compared performance for those busy users and see what happens. This is total throughput. This is on some things I need to update. Point-to-point can be implemented differently. It can be implemented as either simply providing separate cable, like in this picture, or as WDM PON. technology, which I will not spend time on it, but it's called WDM PON, which allocates separate wavelength channel to each subscriber. Idea is same. It's fixed channel. You cannot use more than that channel, but if you don't use it, that channel is wasted. So here it says WDM PON, but really on the picture it shows point-to-point Ethernet. Anyway, 10 gig GPON blue line. This point-to-point architecture is red line. And see by how much capacity throughput in EPON, even though it's only 10 gigabit per second, by how much it exceeded throughput on this network, which has a total of 32 gigabit per second. Also, huge difference in average packet delay. This is average packet delay in this situation, and delay was significantly lower in case of shared capacity. Packet loss, very similar picture. Packet loss was significantly lower if we allow our capacity to be shared among our users. So point of all of that is to develop high capacity network. It's not so important to increase the bit rate as it is important to allow resources to be shared, specifically bandwidth to be shared. The impact of bandwidth sharing is much higher than the impact of increasing bandwidth. And finally, designing access network for quality of service. What is quality of service? Quality of service is simply a way for network to enforce number of parameters that are critical for various applications. One is bandwidth guarantee. You want to ensure that application gets what it needs in order to transmit packets. Voice and video do not degrade gracefully when bandwidth is not enough. FTP does, because FTP can retransmit. You hardly will notice if it retransmits packets. Voice and video, no. You will see artifacts on the screen, or you will hear some clicks on the phone, on voice over IP phone. You need to provide enough bandwidth. Latency and jitter is very important. As I mentioned before, voice, video, all susceptible to packet latency and latency variation, which is jitter. Even if enough bandwidth is given, but latency is not controlled, voice conversation will not succeed. You will not have voice connection. And finally, packet loss. It's clear video has significant artifacts if packets are lost. Transmission control protocol can retransmit lost packets, but for real-time services, it is not. It would not work because usually that retransmitted packet would arrive too late. So here are just some examples of how QoS can be provisioned to support different services. I will not spend time on this. I mentioned before that EPON really, it's easy to think of EPON as distributed switch. There are some peculiarities about EPON. This splitter, this device is very directional. That means that ONUs cannot see each other. Cannot see transmission from each other. They can only receive signal from OT. Because that splitter passes data only in this direction and this direction, but not back here. And similarly, OT can only see signal from ONUs. So if we need to arbitrate that network to avoid data collision in upstream direction, ONUs cannot do any kind of self-arbitration. They cannot pass token to figure out how do we take turn transmitting data. They cannot see each other. OLT always serves as centralized scheduler. If you think that QS is difficult to provide in regular switch, which is all in one box, think how difficult it is to provide on EPON. Here's the impairment. First of all, when ONU is not transmitting, it should shut down laser off. This is done because lasers, even in absence of signal, can generate spontaneous emission nodes. If you don't shut them off, then one ONU will be sending data, and the rest of ONUs will generate noise, and OLT will not be able to receive that data at all. It will be obscured by the noise. So ONUs that are not transmitting have to shut down their laser off. That takes time. This is not instantaneous process. Also, when OLT receives signal from different ONUs, because all ONUs have different lasers, they all located at different distance, that signal will have different amplitude. So OLT has to adjust its gain every time it receives new burst from new ONU. And it also has to synchronize. All that takes number of microseconds, well, maybe 1 microsecond, which is still significant. This overhead is fixed. If you, in order to prevent that overhead from consuming most of your bandwidth in PON, you want to make your transmissions longer. You cannot tell this on you, send me one packet, send me another packet, send me one packet. Letting on you send such short transmissions will increase overhead, because after every transmission, OLT has to wait while one on you shuts down laser, another on you turns it on, and then it has to synchronize on data coming from next on you. It will be very inefficient. So the point is that scheduler should not schedule individual packets. It must schedule larger bursts, maybe 10, 20, or 100 of packets together to maintain efficiency. Second impairment, limited control plane bandwidth. Scheduling each ONU requires, as I mentioned, gate, message going downstream, report message coming back. These messages consume bandwidth. They are in band as any data packet. And that means ONU, for example, cannot send report every time something new happens in ONU. Every time it receives new frame from user, if it sends another report, it will consume entire bandwidth of the phone just by sending these reports and not data. That means ONU should report less frequently and send some aggregated information rather than information about every new packet. And that means OLT has somewhat not obsolete but imprecise information. It may know that ONU has 10,000 bytes together, but it doesn't know what are the packet sizes, for example, inside ONU. And finally, large control propagation delay. ONU and OLT can be up to 20 kilometers away. So about 100 microseconds one way. But this is not that bad actually. What's bad is ONU cannot transmit at any time. ONU has to wait for its assigned time slot. And that maybe ONU will have to wait 2, 3, 4 milliseconds for that. That means that these control messages are not instantaneous as they would be inside one box. They have some delay, sometimes even significant delay. And that results in OLT always operating with somewhat obsolete information. So these are the challenges that EPON has to overcome to support quality of service. And many vendors successfully overcome those challenges to support quality of service, to support IPTV and voice and various other services. one distinction that my company introduced to that technology, as I mentioned, scheduler inside OLT, what's called centralized scheduler, schedules different ONUs. And this is what indeed our competitors do as well. But inside the ONU, each ONU, you usually have multiple queues. Either because there are multiple services, for example, you would allocate one queue for video, one queue for voice, one queue for data, or maybe each ONU serves many subscribers. In this case, each subscriber gets one queue for video, one queue for voice, one queue for data. Traditional way to do it is to have scheduler inside ONU, which schedules multiple queues into one time slot given to that ONU by the OLT. If you do that way, it became clear to us that it's really difficult to enforce fairness between, say, voice queue in ONU number 1 and voice queue in ONU number 2. Because it really was up to that scheduler inside, and that scheduler had no idea what other schedulers are doing in other ONUs. So a solution that Novus proposed, and we actually deployed that in Japan, each ONU pretended to be multiple virtual ONUs. So that now centralized scheduler knows about every service, every queue, and it can schedule them all separately. And this allows us, this flat structure allows us to have fairness of resource allocation across entire cone. Here, fairness was enforced across ONUs, but within ONU, every queue would have different status, and so on application-to-application basis, there was no fairness.
Now, would there be any limitation here, where if your number of subscribers that the ONUs, are so many, and then now the OSP now needs to be aware of all of these and queues and so on?
Scalability question is wonderful question. So typically today number of ONUs is 32. We support about 2,000 of those virtual ONUs. So sometimes in some deployments, you are right, it may be that number of users is so great that we cannot give each user multiple links, virtual links. So we figure out how do we combine aggregate traffic to have you be able to control it. Maybe we give one link to user, and user home gateway will be responsible for scheduling traffic properly. Maybe we give one link, for example, ONU may serve what's called MDU, multi-dwelling unit, where behind ONU there is a switch, and that switch connects to, say, 20 subscribers. Obviously, we cannot give each subscriber a separate connection, in that case, virtual connection. So we would give that MDU separate link for video traffic, separate link for voice traffic, separate link for data traffic. But that puts additional requirements on that big switch to enforce fairness.
Yeah, so this means that if you have, if you are considering that you said 2,000 used for ALT, and then your 32 of these for ONUs, each of 2,000 divided by 32, that's going to be like 64 or so, right? Around 60 something. 2,000 divided by 32. So this is now going to be the number of, the number of queues which can be allocated to each one user, right?
Yeah. Yeah. So fairness is also a critical parameter. Very often, queues will not how do we divide this surplus bandwidth among these EQs? There may be many ways to divide it. It should be some kind of policy provided by the operators how bandwidth can be divided. But point is that it is very critical for operator to ensure fairness of experience to various users. Remember, I started this presentation with comparing Comcast to Fios. Now imagine that two neighbors that both subscribe to Fios or both subscribe to Comcast found out that one has better quality than the other one. That also will be a big problem to the operator. So fairness of allocation, this surplus bandwidth, is very critical as well. So overall, EPON emerged as dominant technology globally, not in US though. Today, about 40 million subscribers are served by EPON. China alone deployed about, I think, 16 million last year. They're going to deploy 20-something million this year. EPON is universal architecture because it can serve all types of users on the same network. It can serve residential users, business, cellular, backhaul. It was designed from the beginning to be able to do that. It can support various configurations: single family unit, MDU, multi-dwelling unit, multi-tenant unit, fiber to the home, fiber to the cabinet, or fiber to the node. And it can support what's very critical, it can support various data rates on the same networks. And in standard, in a typical standard, we spend lots and lots of time and effort to achieve that capability so that you can keep your existing 1 gig or new, 1 gigabit per second or new, and new standard was finished last year, and new devices will appear soon for 10 gigabit per second or new. You can connect them all on the same network, and they will work. PON is also very power efficient. This chart is from Professor Rodney Tucker's presentation he made a number of years ago, which compares various access networks, and you can see PON is this green line is most efficient among all. So why is PON efficient? First of all, there is no electronics in the middle. It's just fiber. All the electronics on the sides. ONUs shut down lasers when they are not transmitting. So that saves power. Single port in central office serves many subscribers. That saves power. And fiber is much more efficient energy guide than copper wire. It simply does not radiate energy around like copper. It just channels it. This is also very important. So what are the future improvements? What are we working on? One is, if you consider typical California residential neighborhood, lots are fairly small, houses are close to each other, so Wi-Fi networks have reliable coverage of neighboring lots. In my house, I can see 6 or 7 Wi-Fi networks from my neighbors. I cannot join them, but I can see them. What if we develop technology which allows Wi-Fi routers in our homes, instead of being owned and maintained by subscribers, be owned and maintained by network operators? Provides very interesting capabilities. For example, if there is a construction and fiber cut, operator may configure this network to use this Wi-Fi router will connect to neighbor's Wi-Fi router and use neighbor's connection to get to the internet. You will hardly notice that your own fiber connection was cut. So we call it protection by neighbor. And it costs nothing to do this protection. Or you can save power using very similar method. At night you may shut down entire ONUs and have your devices in general, problem with shutting down ONU is because next generation networks, or today networks, they serve all types of applications, including voice, including what's called lifeline. If you have some emergency, your phone should always work, no matter what. This is government requirement in all the countries. So shutting down ONUs is a problem, because now ONU also serves your voice traffic. But if we allow this protection for neighbor, then it works.
That's a question out here. For one thing, but the Wi-Fi may not give you enough bandwidth for the video these days.
Well, 802.11n gives you 100 something, 100 plus megabit per second, and there is new one coming, 802.11 something, which is up to 1 gig.
So my question was that whether that one is scalable on one hand. Second, as soon as the traffic from the neighbor comes to you, this means that the fiber which goes to the neighbor now should carry all of the total of the two traffic.
But remember, this is shared capacity. If this fiber cut, this capacity almost by default is given to someone else.
Oh yeah.
So this fiber actually can carry up to entire capacity of entire network. But your point about Wi-Fi is very good. Maybe you will not be able to see as many video channels in parallel as if your fiber is connected, because this link may become bottleneck. Nevertheless, what's important is that your voice connection will work, and maybe with some reduced quality, your video will continue to work. Or maybe instead of being able to see 6 channels at the same time, you only will be able to see 2 channels at the same time. Another work that we're doing, and again, this is related to where I started this presentation. Comcast could not compete with Verizon because Verizon had fiber optic network and Comcast had HFC, hybrid fiber box network. Verizon was bleeding customers heavily. And similar situation with all cable providers. Comcast was bleeding customers. Time Warner in the same situation. Cablevision in the same situation. US cable companies are realizing that they need to upgrade their networks very, very soon. And they're becoming very interested in EPON. But what they're concerned of is they have enormous infrastructure built around existing DOCSIS networks. All the DOCSIS-based billing, all the DOCSIS-based inventory management, all the time servers and TFTP servers and everything else, it's enormous investment that they have. So what they want to do is to develop EPON in such a way that it can be plugged in their overall DOCSIS architecture and be used with everything else DOCSIS. With DOCSIS management, with DOCSIS billing. The only difference is it will use EPON to carry much more bandwidth, many more channels to serve users with more bandwidth so that they can compete with Verizon and AT&T and other operators. So this is another project that we're working on allowing EPON to be used in cable networks. And in new standard, which I'm working in, all cable operators are participating and very, very keen on having this new technology developed. And I guess that's it. Any questions?
First of all, as far as I'm talking about now the EPON and GPON deployment in the United States, and you basically majority of the main operators are using the GPON, and then whereas in China, it's mainly the EPON. Now, how is it that maybe in future we'll be going to the
Yes, you're correct that in US, telcos deployed GPON. This is, in many degrees, very similar technology to EPON. It uses different framing, but it's also sharing, technology based on sharing. It uses single wavelengths in one direction, and single wavelengths in the opposite direction, and very similar. If you look at volumes that's been deployed, Verizon, I think, deployed close to 2.5 million lines. And that's the biggest deployment of GPON anywhere in the world. EPON today probably around 40 million lines. So it's significantly higher. Number of reasons. First, EPON was much simpler, much fewer options, much easier for vendors to develop devices, and much easier to achieve interoperability. So when NTT in 2003 and 2004 wanted to deploy fiber optic network, EPON was the only choice, and they made that happen. And China followed NTT, so today majority of deployments are in Japan and in China and Korea in the third place. What will happen with GPON? Hard to say. GPON is working on next generation technology. EPON is working on next generation technology. But the EPON standard is completed. The GPON standard will be completed soon for 10 gig GPON. Whether there will be convergence, probably not. It's like T1, E1. It's T1 in US, E1 in Europe. Very similar technologies, yet use different data rates. It probably will remain like that with EPON and GPON.
Yeah. And then another question that I have, that the slide that you showed the traffic, these were mainly what, in the upstream or downstream? Because generally in upstream there is not much basically.
You're talking about this one?
Well, no, the previous one, no, not after one. Yeah. Or further down, and then another one. Yes, yeah, this one now. Now, the top one, the blue one, is it what? Is it for the upstream or for downstream or what?
This is synthetic traffic. This is generated using special traffic generators that produce what's called self-similar traffic. It is developed to match what aggregated traffic looks on the network. This is mainly, this could represent video, but not a single flow. Many flows of video aggregated on the same connection. So it's not actually captured traffic, it's generated traffic.
Now, if the main traffic is additive and it's mainly going downstream from the for the upstream streams that basically that come from the different or users, would we have such a big problem?
Well, it's interesting to look historically what happens with traffic.
Yeah.
Traffic was very asymmetric in era of HTTP because you mostly send short requests and you download big page maybe with pictures, photographs. And then when BitTorrent came out, or other sharing applications like Kazaa or something, which rely on parts of files stored on members' computers and streaming upstream, traffic became much more symmetric. And at some point, the studies were showing it was 1 to 4 to 1. So 1.4 downstream, 1 upstream, almost symmetric. And it went from 7 to 1. Now it's becoming asymmetric again because more video coming downstream.
The HTTP, which comes from the nodes in the network.
Yes. So video is asymmetric because you, with your eyes, you can consume much more than you can produce. And most video is going downstream, as you can see. YouTube generates a lot I'm not saying it should be symmetrical, but I'm saying it should be sharing. Sharing is absolutely critical in both directions. Obviously, Netflix and YouTube, they generate very high volumes. In this report, by the way, they also show downstream traffic distribution. I think volume, unfortunately, I don't have latest numbers of how asymmetric it is. My guess would be somewhere around 5 to 6 to 1. Yes, please.
First of all, I was going to thank you for this timely talk.
Thank you.
We actually had a couple of your papers on our reading list about econ. But I wanted to ask you about the split ratio, which we actually utilize on the splitters. Typically, there are some actual research on that, and they are saying that you can go up to 128. And I was wondering, what's the state of that right now? Also, regarding the convergence of WDM systems with PON systems, it doesn't seem like there are a lot of talk about that. And I was just wondering, is it because of the capacity that at access level we don't really need that kind of capacity, or is it still under?
Really two questions, so let me take one at a time. When we talk about splitting ratio, why is it limited at all? It's limited because this device here, which is called power splitter, splits your power. If you have 1 milliwatt coming in and you divide it 16 ways, you have 1/16 going down to each one. There is a limit how sensitive receiver can be in each one. So overall power budget is what determines how much you can split it. You can split it more if you make your links shorter. So even in our system, we tried it with 128 split. It works, but you need to limit your links to maybe less than 1 kilometer. With 20 kilometers, again, depending on optics, it's either 32 or 64. In Japan, their average length from central office to subscribers is only 1.5 kilometers. So one would think, okay, maybe we can have higher split. Unfortunately, they put connector every 500 meters, and every connector takes 0.1 dB when it's clean, and with time it gets dirty, it can be 0.2, 0.3 dB loss in the connector.
Why they put connectors?
Because they do lots of construction, and when there is construction, they want to reroute it around the block. They reconnect it quickly. So that's about split ratio. You want more split ratio, you will need to put amplifiers. In IQT, there is also a project, they want to develop what they call phone extender. That is a device that goes in the middle here, which really makes it not phone anymore. It's a device which recovers and regenerates signal in the middle and sends clean signal, amplifies it and sends clean signal, but it takes power. It's strictly speaking not phone, even though that device has no protocol, no arbitration, it is still electrical device in the middle. Other than that, this is the limit. You cannot split more than 128 in the best case. When we started 10 gig EPON project, we studied all available power splitters and their losses. So that's available somewhere. If you want to find it, I can show you where to find it. So you will see how much loss splitters generate from 1 to 2 to 1 by 28 splitters. Second question was, remind me again.
I was just wondering about the WDM, combination of WDM and EPON.
There are projects like this, especially the one I know were done in F3 in Korea. They call it hybrid PON, where they allocate multiple WDM channels, and then each channel they split using power splitter, and they arbitrate it using regular EPON protocol or GPON protocol. no need for that much bandwidth here. It significantly increases cost. So today, all WDM-based technologies increase cost. It's hard to make them reliable enough for access environment so that when temperature changes, the wavelengths do not drift as much and so on. There is a company in Korea also called Novara Optics that was purchased by LG Nortel that was pioneering this technology, but it is not commercial. Even though it's been deployed in few places in Korea, it is not ready for mass deployment.
Yeah, very good. And now it's now about 10 minutes to 6 o'clock. On behalf of our department and the School of Science and Technology, I would like to thank Dr. Kramer for such an instructive and really useful. I enjoyed it very much. And then very nice slides. So